Last time we talked about 2x4 frame platforms and how they are made up of three structural components. There's the platform, the plywood lid, the 2x4 joists that run across the grain, and then there's the 2x4 girders that run the length of the panel. And that those platforms transfer forces from the plywood to the joist to the girders and then to some kind of legs that have to run down to the ground. And those legs would want to be at 4-foot distances from each other along those 8-foot girder members. But we didn't talk about really legs at all and what that means and how to make them and how to think about them. So that's what we're going to do today. We're going to talk about legs. We're going to talk about three typical platform leg techniques for 2x4 framed platforms. 2x4 leg, a 4x4 leg, and then, depending on how you call it, a black pipe, an iron pipe, or a Schedule 40 pipe leg. Those are the three most common, at least that I'm familiar with. So let's talk about 2x4 legs first. So previously we were dealing with wood as a bending member that, for resisting tangential stresses. And wood is pretty good at that, but it's a little bendy, and that matters when we start talking about using wood in axial loads and resisting compressive stresses. It's actually really, really good at that, except that it is a little bendy. And when columns are under compression, they fail in two ways. And I have a little thing here to show you about that. They fail in compression or crushing, which is literally just like stepping on a tin can, crushing straight down. But they also fail due to buckling. And buckling is the tendency when under a compressive load of a member to try to bow out in the side like that. I hope you can see that on the camera. Because wood is bendy, it's prone to buckling. So again, under compression, columns have a tendency to bow out to the side. Some materials are better at resisting bending and buckling than others. So later when we talk about iron pipe and steel, we'll see that it's pretty good at resisting that. Wood is less good. And some shapes resist bending and buckling better than others. And that seems weird, right? But what does shape have to do with it? When we talk about shape, we're talking about the cross-sectional shape. So not looking at it this way, but this way, the cross-section. In this case, a little, looks like 3/16 by 3/16 square shape. Why does that matter? Well, just like in bending, because buckling really is bending, don't tell anybody I said that, it's a big secret. Just like in bending, the amount of material on either side of the midline of a column impacts how well that column resists buckling in that direction. So a 2x4 is more likely to buckle across the thinner 1.5 inch width than across the thicker 3.5 inch width. That's a lot of words. It doesn't always make sense as words. So let's try to look at it as a picture. If we imagine this is a 2x4, right, as a column, right? This width here is 1.5 inches, and this width here is 3.5 inches. There's more material in this plane than there is in this plane. And because of that, we're more likely to buckle coming out in this direction than we are in this direction. I hope that makes sense. It's because of the amount of material that's there to help resist bending and buckling. All right, so that's important for us to know because it has to do with, it's going to inform some of the things that we're going to talk about here in a little bit. So the National Design Specification, the National Design Specification provides some data and equations to determine the strength of a 2x4 when used as a compressive member. If we ignore buckling entirely, just forget about it, pretend it doesn't exist, if we consider just the ability of that material to resist crushing, wait for it, this is wild, a number 2 Eastern White Pine 2x4, and I picked Eastern White Pine because it's the weakest species dealing with compression parallel to the axis of the grain. A number 2 Eastern White Pine 2x4 could carry a load of nearly 5,000 pounds. That's whether it was this tall or whether it was 12 feet tall. Just crushing loads. Amazing. Except that buckling and compression are synergistic. Right, so as a member starts to buckle, the loads are now no longer right in the axis, the main axis of this member, which means it can't handle compression as much, which means it's going to buckle a little bit more, which means it can't handle compression as much. We get this thing that's sort of cascading. And so buckling and compression aren't really able to be divided from each other. According to the NDS, when we account for the impact of buckling on compression, a 2x4 column made of number 2 Eastern white pine without any bracing at 1 foot tall can support a compressive load of about 4,775 pounds. At 2 foot tall, it can support a compressive load of a little less, 3,900 pounds. A 4 foot tall 2x4 of number 2 Eastern white pine could support a compressive load of 1,500 pounds, more or less. And an 8 foot tall 2x4 of number 2 Eastern white pine could support a compressive load of approximately 415 pounds. That's still pretty strong, right? That's pretty great. But notice that as we get longer, the tendency to want to bow and buckle gets greater, right? It's not as great here as it is here, as it is here, as it is here, right? And that impacts its ability to resist compression because of the synergies between compression and buckling. But we still haven't talked about resisting the buckling all by itself. I know that seems a little weird, but first we just talked about compression, no buckling. Then we talked about how buckling and compression impact each other. But now we're going to talk about the ability to resist buckling all by itself. A compressive member's ability to resist buckling is dependent on the cross-section of the member and its strength, like we talked about. When looking at 2x4 legs, we express this as the ratio of the length of the column to the smallest cross-sectional dimension. In the case of a 2x4, 1.5 inches, the slenderness ratio, L over D. The ratio of length to depth, L over D, the slenderness ratio, according to the NDS, must be less than or equal to 50, or we can't use it as a compressive member. If the ratio of L to D, the slenderness ratio, is larger than 50, we've got to add some bracing to ensure that the total or the longest length that's not braced in that leg takes that slenderness ratio to under 50 again. That's a lot of words again, so let's talk about this here. So let's imagine we have a 8 foot tall 2x4 column. So the length is 8 foot tall, and we know that the smallest sideways dimension is 1.5 inches. In that case, L over D is 8 over 1.5, except we need to think about it in inches. So we're going to say it's 96 over 1.5. 96 over 1.5 is 65. It's too big. I can't use this according to the NDS. Even though it can hold up 415 pounds in compression, it's likely going to buckle if we get even anywhere near to that. So we need to do something to prevent that. So we'll need to add some kind of cross bracing so that our unbraced length, the length that isn't braced, never causes a slenderness ratio of above 50. So, just some facts. An unbraced 2x4 column at 1 foot tall has a slenderness ratio of 8. That's 12 over 1.5. At 2 feet tall, it has a slenderness ratio of 16, which is 24 over 1.5. At 4 foot tall, it has a slenderness ratio of 32. And as we just talked about, at 8 feet tall, it has a slenderness ratio of 65. Suddenly, I'm too tall without some kind of bracing. So the tallest unbraced 2x4 column that would pass the slenderness ratio test is 75 inches, or just over 6 feet. 75 divided by 1.5, L over D, is 50. So that's the tallest 2x4 column unbraced that we could, that passes the slenderness ratio test. What does that mean, unbraced? We should really unpack that a little bit more. So we now know that up to here, not to scale, is 6 feet. That length, totally fine without any bracing. But when we get to 8 feet, it's too much. So we've got to add something here and here to brace this column so that it won't buckle. And it shortens the unbraced length here to 6 feet, if that makes sense. I hope so. And we could do that here and down here or wherever, as long as the total unbraced, the longest unbraced length is less than 6 feet. Okay, so for 2x4 legs, when placed as dictated by the platform construction and when joined properly to the platform framing, more about that later, a 2x4 leg can carry significantly large loads, well over 400 pounds at 8 feet in height. The 2x4 legs must be braced appropriately, like this, as we just talked about, such that there is no span larger than 6 feet without bracing. And bracing must be added to support the possibility of buckling across the 1.5 inch width. So this is what we just talked about here. I don't need bracing here because that 3.5 inch dimension keeps it from buckling in that plane. And we have to make sure we're resisting the buckling in either direction. So again, here and here. Great. That's a 2x4 leg. That's all we need to know to use a 2x4 leg appropriately, except for that key thing about joined properly. More on that again later. 4x4 post legs are another really common lumber leg for a 2x4 framed platform. 4x4 post legs follow the same rules as 2x4 posts. The only differences are the species grade of post material and the cross section of that post, right? So the NDS, all the same rules apply. We're just dealing with different materials potentially and a different D size in each plane of that 4x4 cross section. So at 4 foot tall, because we're bigger, we're now 3.5 by 3.5, the slenderness ratio of a 4x4 post is about 13.7, something like that. At 8 foot tall, the slenderness ratio of a 4x4 post is something like 27.5. The tallest 4x4 post that satisfies a slenderness test of L over D being less than 50 is 175 inches, or 14 foot 6. That's like 14 foot 5.5 or something. So we can get a really tall 4x4 post without any need for bracing that to resist buckling, which is kind of fantastic. And in terms of load capacity, a 4 foot tall 4x4 post, including buckling and compression, has a total capacity, number 2 Eastern White Pine, of almost 10,000 pounds, which I promise you will never load up on a 2x4 framed platform. That's our 4x4 leg. Again, when placed as dictated by the platform construction and when joined properly to the platform framing, a 4x4 leg can support significantly large loads, well over 4,400 pounds at 8 feet in height. That's like 10 times what we were seeing in a 2x4 post. 4x4 legs must be braced appropriately such that there is no span larger than 14 foot 6 inches without bracing, and bracing must be added to support the possibility of buckling across both directions because it's a square, so it's going to buckle in either one equally, and bracing must resist that possibility on all 4 sides. So 2x4 legs and 4x4 legs function pretty much the same way in terms of buckling, but the capacities are a little different, as we just talked about. The third kind of leg I see all the time for 2x4 framed platforms is Schedule 40 pipe, also known as black pipe, sometimes known as iron pipe. It comes in a bunch of different sizes. You might see an 1.25 inches or 1.5 inches. We'll talk about 1.5 inches here today. Similarly, we have to worry about capacity for compressive stress and also buckling and slenderness. This time we're going to look to the Steel Construction Manual, which provides equations and values for determining the strength of pipe legs. So we're going to think about the slenderness criteria for bracing against buckling, and then the overall capacity to resist compression. Like lumber columns, iron pipe must satisfy our slenderness criteria. It's a little different this time. This time we're going to talk about L over R being less than 200. L is still length. R is radius of gyration, which is, you're going to hate this description because it sort of references itself, but radius of gyration is a mathematical representation of a member's ability to resist buckling in a weird way. So L over R is kind of equivalent to L over D. And frankly, the only reason we're using a different number, L over R over 200 versus L over D of 50, is in part because D is a mathematical evolution of L over R based on the fact that in sawn lumber we're dealing with rectangular shapes. None of that really matters. We just need to know that L over R has to be less than 200. And we can look up R. We don't have to figure it out. We can look it up in tables that are provided in the Steel Construction Manual and are frankly available for free online. if you just do a Google search. For 1.5-inch black pipe, we can look up and find that the radius of gyration is 0.626 inches, 0.626 inches. So then, at 1 foot tall, a 1.5-inch Schedule 40 black pipe leg has a slenderness ratio of about 19, much lower than 200. At 8 foot tall, that same pipe has a slenderness ratio of 153, still much lower than 200. The tallest 1.5-inch Schedule 40 pipe leg to satisfy the slenderness criteria of L over R must be less than 200 is 125 inches, or just less than 12'6". Not quite as tall as that 4x4 post, but pretty tall. A 12'6" leg would satisfy our slenderness criteria. According to the Steel Construction Manual, when we account for the impact of buckling and compression in an 1.5-inch Schedule 40 pipe leg without any bracing, at 1 foot tall, it can support a compressive load of approximately 13,200 pounds. At 4 feet tall, it can support a compressive load of approximately 10,440 pounds. And at 8 feet tall, it can support a compressive load of approximately 4,800 pounds, really close to that 4x4 post. So just in terms of comparisons, that 1.5-inch pipe here can support, about this size, can support the same load at 8 feet as that 4x4 post, which gets a lot bigger. So we might consider which one might look better, for example. Okay, so 1.5-inch Schedule 40 pipe legs, when placed as dictated by the platform construction, so for a 4x8 platform once every 4 feet along that 8-foot length, when joined properly to the platform framing, can carry significantly large loads, well over 4,800 pounds at 8 feet in height. It must be braced appropriately, such that there is no span larger than 12'6" without bracing, and bracing must resist the possibility of buckling all the way around or on 4 sides, which would be sufficient. Okay. So we kept saying, when placed as dictated by the platform construction and when joined properly to the platform framing. Okay, we got to talk about that, right? It's key. So, 1, legs should be in compression or under the framing. And I'll tell you a thing I see all the time. In fact, I was just watching a show the other day and I saw this. You've got your 2x4 framed platform here. I'm going to just draw pieces of it. We don't need the whole thing. And the leg is in here and bolted through the sides of the frame. Seems like it would make sense. That's the easiest way to secure it. We just use some bolts. Except we've got a couple of things that could happen here. 1, we're putting all the forces into the joint now. So this frame isn't really resting on that column as much as it's resting on a bolt or multiple bolts that are then in the column. And so those bolts are now seeing a shear load. And we want to avoid that whenever we can. Second, when they're in that situation, we've now put holes in the lumber, and then we've put, it's round shaped, but it's still kind of a wedge in that lumber that could cause the lumber to split along the grain. And we do kind of see that over time. Those holes get bigger. They kind of wiggle around and get larger and elongate in the vertical dimension when we secure platforms like this. Third, if we're not careful, because that frame is going to sink a little bit, if that post is pressed up against the lid of the plywood, of the platform, that plywood lid, it's going to start to cause that plywood to peel away from the frame. And now suddenly the plywood's not supported by anything other than just in the corner on that post. Not good. All of that is bad. So what we want to do is, instead of putting that column inside the frame, we want to put that column here underneath the frame. And specifically underneath the ends and the middle of that 8-foot member. And then use some kind of a mending plate or a piece of material to help us span the seam and screw into both the post and the frame to hold it in place. So that's number 1. The legs really want to be in compression. And it should be placed based on the framing above, as we just talked about. So every 2 feet along that 2x4 beam. And all of our calculations that we've talked about for compressive loads and buckling are all based on assuming purely pinned connections, which means that these can rotate fully, right? That leg can just do this easily. Joints must be supported and braced to resist rotation, and that's different than the bracing to resist buckling. They can be used functionally in the same way, but we're thinking about it as two different things. Just because we've solved the buckling bracing doesn't mean that we've solved the cross bracing to resist rotation. And those cross braces must be sufficient in length and size to resist any potential lateral loads. We're going to talk more about cross bracing in a later video. So that's kind of it for today. We've talked about 2x4 legs, we've talked about 4x4 legs, we've talked about 1.5" Schedule 40 legs and the capacities that they have, and how we have to think about bracing for the unbraced length and the buckling capacity of each. Thanks.